Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. We are still in section 4.3, and in this lecture we will talk about the second derivative test. In the first derivative test, we have seen how to use the first derivative to determine the local extreme values, uh, and here we will use the second derivative, f double prime, to determine or test whether a critical number is local minimum or local maximum. The condition is that if the derivative is zero. So the second derivative can be used only for the zeros of the first derivative. The numbers that make the first derivative does not exist are not used here. So this test is only for the zeros of the first derivative. So to use the second derivative test, you have to find the first derivative and its zeros, and then substitute with these zeros in the second derivative. If you find that if double prime of c is greater than 0 is positive, then f has a local minimum at c. And if the second derivative is negative at c, then f has a local maximum at c. So if it is positive, local minimum. If it is negative, local maximum. Notice here, this is f, this is the graph of f. And when we say that f double prime is positive for in part A, if double prime is positive, we know that the graph of f would be concave upward. So if the graph of f is concave upward, and at P, at a point P, where x is c, you find that f prime at c is 0. So this means that the tangent, the slope of the horizontal, the slope of the tangent line is 0. So the tangent line is horizontal. And if the tangent line is horizontal, this means that the point is minimum. So this will help you to understand why if the second derivative is positive, we conclude that we have a local minimum at c because of this. Note the second derivative test is inconclusive when f double prime equals to 0. So if you substitute with c and you get equals to 0, you don't get greater than or less than. You just find that the second derivative at c is 0, then no information is given from the second derivative test, and you have to go back to the first derivative test. So at such a point, there might be a maximum, there might be a minimum, or neither. So the test fails, okay, in this case, when the second derivative is 0. It also fails if the second derivative does not exist, okay. In such cases, you have to use the first derivative test. Let us see this example. Discuss the curve with respect to concavity, points of inflection, and local maxima and local minima. Well, let us find the first derivative. And let us find the zeros of the first derivative. I can take 4x squared as a common factor. So I have zeros of y prime. 0 is a 0 of multiplicity 2, and 3 is a 0 of multiplicity 1. These are the zeros of y prime. These are critical numbers of y because the domain of y or real numbers, they belong to the domain. So these are critical numbers of the function. So we can use the first derivative test to determine whether we have local minimum, local maximum at 0 and 3. And I can use the second derivative test. So let us try to use the second derivative test. To use the second derivative test, I have to find y double prime. I'll find it from here. So it's 12x squared minus 24x. Now, if I replace y double prime, if I find y double prime at 0, this number, I get 0. Okay. So y double prime does not tell me anything about 0 when x is 0. So I don't know what happens when x is 0. I need to use the first derivative test. But for 3, let me replace x by 3 in the second derivative. So 12 times 9 minus 24 times 3, I'll have 36. And 36 is greater than 0. So because the second derivative is greater than 0, there will be a local minimum at x equals to 3. So I know immediately that the local minimum is f of 3. And to find f of 3, or you can say in this case y of 3, because it is called y, not f here. So I replace x by 3. So 3 to the power 4 minus 4 times 3 to the power 3, and that's negative 27. So actually, negative 27 is a local minimum of this function. Now, to find out what happens at 0, I need to use the first derivative test. And to use the first derivative test, if you remember, we draw this table, we make this table from negative infinity to infinity. I put the values, the zeros of f prime, 0 and 3, the two numbers, and I find the signs of f prime in these three intervals. Well, y prime, again, I write it y and not f. So y prime has degree 3. Okay, so I can't. I have to. I look here. This is also y prime. It has the same signs as y prime. So if I choose a number greater than 3, 4 minus 3, 4 squared is positive. Now 3 is a 0 of multiplicity 1, so I'll have here negative, but 0 is a 0 of multiplicity 2, so the sign does not change around 0. So here I have the function is decreasing and here the function is increasing. And I can see also from the first derivative test that 3, I have a local minimum at 3. So really y of 3 of or negative 27 is the local minimum. But at 0, I notice that decreasing, so nothing at 0. So I have neither local minimum nor local maximum at 0. And I got this from the first derivative test. All right. So discuss the curve, points of inflection, local maximum, local minimum finished. Now he needs concavity and points of inflection. And to talk about concavity, I need to find the zeros of y double prime. So I put y double prime equals to 0. I take 12x as a common factor. I have x minus 2. All right. So the zeros are 0 and 2 of f double prime. So this is 0, this is 2, and this is negative infinity to infinity. The domain of f is all real numbers. It's a polynomial. Here y double prime and here y. And I now check the signs of y double prime. Y double prime has degree 2, so between the zeros it would be negative, opposite to the sign of x squared. And here it is positive. So concave up, concave down, concave up. And I have two inflection points. So the inflection points are 0 and f of 0, and f of 0 or y of 0 is just 0. And also at 2, and y at 2 is 2 to the power 4 minus 4 times 2 to the power 3. and that's negative 16. So these 2 points are inflection points, and I have the function y is concave up from negative infinity to 0, union from 2 to infinity, and concave down from 0 to 2. So by this we answered the question. Now some exercises. Find the local maximum and minimum values using both the first and second derivative tests. Which method do you prefer? Okay, so let me use the first derivative test first. So first I will use first derivative test. So to use the first derivative test, I find f prime now. Well, f prime is 6x minus 6x squared. And I can take 6x as a common factor, and I have 1 minus x. So the zeros of f prime, of course, f is a polynomial, the domain all real numbers. The zeros are 0 and 1. 1 minus x equals to 0 means x equals to 1. And now let me do the first derivative test. To do that, we check the signs of f prime. Now, f prime has degree 2 and the coefficient of x squared is negative, so here between the zeros, the sign of f prime would be positive. So here decreasing, increasing, decreasing f. So I have local maximum at 0. Sorry, local minimum. Local minimum. The local minimum is f of 0 and f of 0 is 1. And the local maximum is f of 1, and f of 1 is 1 plus 3, 4 minus 2, 2. So this is the first derivative test. Now let us use the second derivative test. Second derivative test. To use the second derivative test, I find f prime. Well, f prime is 6 minus 12x. And now I have two numbers, two zeros for f prime, 0 and 1. So I find f double prime of 0. If double prime of 0 is 6, that's greater than 0. So there is a local minimum at x equals to 0. And this is correct. We found that f of 0 is 1 is the local minimum. And if double prime of 1, I replace now x by 1. So I have 6 minus 12. This is negative 6, and this is less than 0. So I have a local maximum because the second derivative is less than 0 at x equals to 1, which is also correct because f of 1, which is 2, is the local maximum. Which in this case, well, I find that f double prime is easier. Okay, using the second derivative test in this case was easier because f double prime was easy to find, and so that's the answer of question 29. Let us check now question 30. Same, find local maximum, local minimum using the first derivative and use the second derivative tests. So let me first use the first derivative test. For that, we need to find f prime of x. And for this function, I have to use the quotient rule. Derivative of x squared is 2x times the denominator. Derivative of the denominator is 1 times the numerator. I have 2x squared minus x squared, that's x squared minus 2x. So this is the first uh, derivative. I can find the zeros of the numerator and the zeros of the denominator. Notice that the domain of f consists of all real numbers except 1. So it's from negative infinity to 1, union 1 to infinity, because 1 makes the denominator 0. So 1 of 1 in the first derivative, it makes the first derivative does not exist, but it is not a critical number because it's not in the domain of f. So f prime is 0 if x, if I take x as a common factor from x squared minus 2x times x minus 2 is zeros. So when x is 0 and x is 2, these are the two zeros of f prime. To use the first derivative test, well, notice that x minus 1 all to the power 2 is always positive, okay? So I'm not going to consider 1 here because it does not affect the sign of f prime. Well, I have 0 and 2 from negative infinity to infinity. But for when you say, when you find increasing and decreasing, you have to make sure that uh, 1 is not there, okay? Because it's not in the domain. So where is f prime? Yeah, this is always positive. So it depends on the sign. The sign of f prime depends on the sign of the numerator. The numerator is degree 2. Between the zeros, the sign is negative. So here the sign is negative. Here the sign is negative. And here the sign is positive. So the function is increasing here, decreasing here, decreasing here, and increasing here. So f of 0, there is a local, the local minimum is f of 2. At x equals to 2, we have a local minimum. So it's 4 over 2 minus 1. So that's 4. And local maximum would be f of 0, which is 0. So f of 0 is a local maximum. F of 2 is a local minimum using the first derivative test. Now to use the second derivative test, I have to find y double prime. And y double prime or f double prime, I will use this one, okay? So I'll find the derivative of this function. I have to use the quotient rule again. Derivative of x squared minus 2x times x minus 1 to the power 2 minus the derivative of the denominator, which is 2 times x minus 1 times 1 times x squared minus 2x. And now to simplify the numerator to find the zeros of f double prime, well, you don't have to simplify f double prime if you like. You can just replace f double prime by 0 and 2 like this, okay? If you want to simplify, it's okay. If you don't want, also it's okay, because all what I need to find, all what I need to know is f double prime at 0, is it positive or negative? But pay attention when you substitute like this. It's not easy to substitute like this, okay? But for sake of uh, fun, I will find f double prime in simplest form. So let me take x. I can take 2 as a common factor from 2x minus 2, because this can be written as 2 times x minus 1. Oh, there, okay. So if it is 2 times x minus 1, so I will take it as a common factor because it's there, here and here. And what I left with would be x minus 1 to the power 2. And okay, let me write it, x minus 1 to the power 2. And then minus 2x minus 1 have been taken, and I have x squared minus 2x over x minus 1 to the power 4. I can cancel x minus 1 with one of the x minus 1s in the denominator. So I'll have x minus 1 to the power 3. Okay. And now I have, let me expand this. It's x squared minus 2x plus 1. and minus x square, and minus times minus plus 2x. Now I see that x square cancels and negative 2x even cancels. That's nice. So I have only 2 times 1. So f double prime is just 2 over x minus 1 to the power 3. And now I can find f double prime at 0 easily. In fact, it is uh, negative 1 to the power 3 is negative 1, so it's negative 2, less than 0. So I must have a local maximum at x equals to 0. Is it the same? Yeah, we have maximum at f of 0. And also, let me check the second 0 of f prime, which is 2. What happens when I replace x by 2 in the second derivative? 2 minus 1 is 1. So it is 2, it's greater than 0. So there must be a local minimum at x equals to 2. Same answers, but I guess in this case, the use of the first derivative was easier because it took a lot of time, not a lot of time, some time to find f double prime. Let me solve one example about curve sketching, and we will continue exercises about curve sketching in another video. So curve sketching, after we find all of this information from the first derivative and the second derivative, we can also use information we know before, uh, add all of them together and sketch the curve. So for example, the first thing always to sketch the curve is to make sure that I know the domain of the function. Well, this function, the domain of this function would be all real numbers, except I have problem with the 0 because 1 over 0 is not defined. So it would be all real numbers except 0. So from negative infinity to 0, union from 0 to infinity. I know that the graph of the exponential function consists of all real numbers, so I have no problem with e to the power x. But since here e to the power 1 over x, so x cannot be 0. Okay. Also, I can check uh, the vertical asymptotes. And if you remember, to find the vertical asymptotes, we find the limit when x, we try to find, okay, what happens when we find the limit when x approaches 0 from the right and from the left. Because 0 is not in the domain. So any number which is not in the domain, we think whether is it a vertical asymptote or not. So to find out, we need to find the limit when x approaches 0 from the right and from the left. Well, I replace x by 0, but 1 over 0 is infinity, and e to the power infinity is infinity. So there is no vertical asymptote for this function because 1 over 0 is infinity and e to the power infinity is infinity. Let me check what happens when I choose 0 from the left. Is there any difference? 1 over 0 is infinity. Yeah, but we would like to know whether it's positive infinity or negative infinity. So that's important because limit 1 over x when x approaches 0 from the right, okay, 1 over 0 is infinity, but we have to find out whether it's positive infinity or negative infinity. And to do that, we replace x by a number greater than 0.1. The sign is positive, so we understand that the limit of when x approaches 0 from the right is infinity. But when I find the limit when x approaches 0 from the left, so the limit of 1 over x when x approaches 0 from the left, 1 over 0 is infinity, but it could be negative infinity. When I replace x by a number less than 0, because I'm coming to the left from the left of the 0, so negative zero point 0.1, I notice that the sign is negative, so the limit of 1 over x is negative infinity. And this is correct, and we studied this in the beginning of the course. And you know the graph of 1 over x. So when you approach x from the right, the function goes to infinity. But when you approach x 0, I mean, when you approach 0 from the right, when you approach 0 from the left, the function, the y, goes to negative infinity. And so the limit when x approaches 0 from the left of e to the power 1 over x would be e to the power negative infinity. And actually, e to the power negative infinity is 0 because this is the graph of e to the power x. Okay, limit e to the power x when x approaches negative infinity is 0. So I find from here that x equals to 0 is a vertical asymptote. Actually, from here, okay? From here, x equals to 0 is a vertical asymptote, not from here. Because this is the definition of the vertical asymptote, okay? Let me remind you the definition of the vertical asymptote. If you find that limit when x approaches a from the right or from the left of f of x equals positive or negative infinity, then x equals to a is a vertical asymptote. But here from the left, this will help me also in the graph because I know now when x approaches 0 from the left, it's not infinity or negative infinity, it would be 0. So I can start graphing if you like. I will sketch the graph here. I have an information, a nice information now. I know that this line is a vertical asymptote. And I know now when x approaches 0 from the right, the function goes to infinity. So the graph will go to infinity here. But when I approach 0 from the left, the curve approaches 0. So actually, it approaches 0. Okay, it becomes closer to 0. But notice that 0 is not in the domain, so there must be an open circle here. So I'll make sure that I have an open circle here because 0 is not in the domain. All right. So this is the information we have up to now. We did not use calculus yet. Okay, what about the horizontal asymptotes? To find the horizontal asymptote, we find the limit when x approaches infinity and negative infinity. Well, whether x is infinity or negative infinity, 1 over infinity or negative infinity is 0, and e to the power 0 is 1. So there is no difference, in fact, between x goes to positive infinity or negative infinity. So this means that the line y equals to 1 is a horizontal asymptote. So this is another information. Let us put it on the graph. So if this is 1, this line is a horizontal asymptote. Y equals 1. So when x approaches infinity and negative infinity, the curve becomes closer to this line. So it seems to me that the curve will continue like this in this part. Good. Now we found the domain, the asymptotes. Now we are ready to find f prime. Well, f prime is e to the power 1 over x times the derivative of 1 over x, which is negative 1 over x squared. So f prime is negative e to the power 1 over x squared. Notice that 0 is not in the domain. Okay, so it's not a critical number. Uh, Also notice that e to the power 1 over x is always positive. So negative e to the power 1 over x is always negative. So f prime is always negative. And this means that f is decreasing from negative infinity to 0, union from 0 to infinity, because 0 is not in the domain. And no zeros of f prime. E1 over x will not be 0 ever. So no critical numbers. So no local extremes. No local extremes. Okay, no local maximum, no local minimum. All right. The function is always decreasing. So yeah, it is here. This, if the graph is like this, it is decreasing. And it has to be like this then, because it has to approach the horizontal asymptote from the right. When x approaches infinity, we have seen it goes to 1. And from the left, the right of 0, it goes to infinity. So it seems that this is the graph of the function. It's decreasing here, decreasing here. Everything is fine. No extreme values. Well, let us find the second derivative. See, maybe there are more information from the second derivative. Finding the second derivative, I will use, it's okay, I will use this one. So I'll use the quotient rule, x squared to the power 2, x to the power 4. The derivative of the numerator, negative e to the power 1 over x, times the derivative of 1 over x, which is negative 1 over x squared. All of this is the derivative of the numerator times the denominator, which is x squared. All right. Minus 2x is the derivative of the denominator times negative e to the power 1 over x, which is the numerator, equals, let us simplify, x squared cancels with x squared. Negative times negative is positive. I have e to the power 1 over x as a common factor. I'll have 1 here, okay, from the first term. And here I have minus times minus, that's plus 2x, because e to the power 1 over x is a common factor over x to the power 4. So this is f double prime. 1 of e to the power 1 over x is always positive. X to the power 4 is always positive. So the only zero of f double prime is the zero of 2x plus 1, which is negative half. So negative half, and this is 0, negative half around negative half, f double prime will change its sign. So if I choose a number greater than negative half, 1 for example, f double prime would be positive. So it's positive here, and negative here. So it's concave down here, concave up here, and concave up here. So now this will change a little here. The function has to be concave down until negative half. Well, if this is negative 1, so negative half, this point now, the function is concave down, that's correct. But from negative half to 0, the function has to be concave up. Okay, so it doesn't approach the 0 like this. It approaches the 0 like this. Okay, concave up. So it's concave up from negative half to 0, but concave down from negative infinity to negative half, and it's concave up from 0 to infinity. So now the graph is absolutely correct, and all the information we found from the second derivative, from the first derivative. And you notice inflection point, I have an inflection point at negative half and f of negative half. And you notice that f of negative half is a small number, it's less than 1, but let us check it, let us find it. So it's e to the power 1 over negative half, so it's negative 2. And if you find e to the power negative 2, that's just 0.14. Okay, so it's a very small number here. So that's the graph of this function. I hope you enjoyed putting all the informations together and sketching a graph of the function. We will do more exercise about curve sketching in another video. Enjoy.